Hello everyone and welcome to your Chem 113 review on quantum numbers. My name is Jason and I work for the ASU Tutoring Centers. Now quantum numbers are essentially used to characterize the electrons in an atom. As we will discover further on in upcoming videos, each electron in an atom has a certain configuration of quantum numbers that perfectly describes it. So no two atoms will have the same four quantum numbers. There are four quantum numbers that we want to know about. In this video, we'll be discussing three of those quantum numbers. And those three quantum numbers give us insight into these different aspects of electrons, which include shells, and then subshells within those shells, and then orbitals within those subshells. Whew. So, okay, let's talk about shells. Shells, these sort of represent how far you are away from the nucleus. So as we've mentioned previously, the electrons exist in these sort of quantized energy levels. So they exist in energy level 1 or 2 or 3 or 4 or 5. There's not a spectrum for them to live on. They live in quantized, like, discrete packets of energy levels, okay? And these energy levels, we call them shells sometimes. You can figure out exactly where you are using the principal quantum number. That's the first quantum number we will talk about. Quantum number. It's denoted by N. And the principal quantum number essentially tells you what shell you're in. It tells you how far you are from the nucleus. So this is which shell you are in. If you imagine electrons orbiting around the nucleus, the principal quantum number tells you which orbit you're in. So are you where Mercury is, where you're the closest to the sun, or are you where Venus is, where you're the second closest to the sun? So as the principal quantum number increases, you get further and further away from the nucleus. Okay, you tend to get further and further away from the nucleus. Okay, so that's what the principal quantum number tells you about an electron. And then from your principal quantum number, you get your secondary quantum number. And this is often denoted by an L. So your secondary quantum number essentially tells you the shape of your subshell. So you have a shell, you know the general area that your electron exists in. But within that shell, there are certain regions that your electron can exist in particular. So the idea here is, in our case, we have n equals 4, right? So the number of subshells we can have is always one less, okay? So it takes on values anywhere from 0 to 1 less than n. So for n equals 4, we have the following possible values for L. We can have L equals 0, 1, 2, or 3. So you start at 0 and you can go up to n minus 1. You can go up to 1 less than your principal quantum number. And for each of these values, we actually don't usually write them as numbers. We correspond them to letters. So instead of writing 0, we often write S. Instead of writing 1, we often write P. 2, we often write D. And 3, we often write F. Okay? So within the fourth shell around your atom, you can have these 4 different subshells. You can have the subshell 4S, 4P, 4D, or 4F. These are all of your subshells. So the 4 in the beginning of all of these represents what shell you're in, and then the S, the P, the D, and the F represents what subshell you are in within that shell. Okay? The S orbitals, they tend to look kind of like just circles. So here's your nucleus. And the idea is, there's an equally likely chance that your electron will be anywhere sort of around that nucleus. The p orbitals look more like dumbbells or hourglasses. They look more like that. So what this means is your electron, if it's in the 4p orbital, it will likely be within this region. It'll very likely be within this region. Okay, so if you take snapshots of your atom at any point in time, the electrons in the 4p orbital will typically, be within this region. Occasionally they can pop out, but for the most part, they stay within this region. The D and the F orbitals get really weird looking. I don't exactly remember what they look like, but I vaguely remember that like the D orbital looks something like, it's like a donut with like a thing sticking out of it. So again, what this means is you are most likely to see your electron within these weird regions. And then the F orbital, again, I'm not exactly sure what it looks like, but it tends to have like a bunch of weird looking different things sticking out, if I vaguely remember, something like that. But they get really weird looking in the D and F orbitals. But again, they sort of represent the regions where you're likely to find your electron hanging out. And because we're in the 4 subshell, we're going to be further away. So if we were to take a comparison of what, say, the 3s orbital looks like, so the 3s subshell and the 4s subshell looks like, the 3s might look something like this, whereas the 4s might look something like that. So it's bigger. So as you get further out, as you increase your principal quantum number, you get further away from your nucleus. And again, don't think of this as like you're orbiting around. The electron is not orbiting around like Bohr thought. In reality, the electron can just appear anywhere within this region. It's just that because we're up a principal quantum number, the electron is more likely to appear further out than it is for a 3s orbital. Okay, so don't think of these as like your electron exists on this outer region, or even for like the p orbitals, it exists like, in this figure 8 region. It can exist anywhere within that figure 8 region, or within this S region. The region is just meant to say, hey, your electron will 99.999% chance that it's going to be found within that region. Okay, so that's what subshells are. So subshells, once you have the shell that you're working with, the subshells give you the different shapes that your electron could possibly orbit within. Okay, so that's what a subshell is. So for the principal quantum number 4, these are your 4 different types of subshells for S, P, D, and F. So we have now answered question number 1 and question number 2. For question number 3, we need to define our 3rd quantum number, and this one is called the magnetic quantum number. And its symbol is often M sub L. Okay. This one describes the orientation of each orbital in space. Orbital. Okay, so we're getting more and more specific. So we had shells, and within those shells we have subshells. Within each subshell we now have orbitals. So for instance, let's look at like the 4p subshell. Remember I said it has sort of an hourglassy shape to it? Well, there are 3 different directions that hourglassy shape can go in. It can go in the x direction. It can go in the sort of, I guess, the y direction. Like imagine this going back into the page. Or it can go in the z direction. Right? There's 3-dimensional space, and this p orbital can go in any 3 of those. So we are in the 4p subshell, but within that subshell, within this shape, this hourglassy looking shape, our orbital can align itself in different configurations. So the subshell has a bunch of tiny orbitals within it, and those orbitals are the specific orientations. So when you hear the word orbital, that goes beyond just the subshell. It says the subshell and actually the specific orientation that we are in within that subshell. That's what an orbital is. Okay, so we're just getting more and more specific as we go down. Principal quantum number just says, how far away are you from the nucleus? Secondary quantum number says, okay, what shape is your electron likely to be hanging out within? And then the magnetic quantum number then says, okay, so that's what the shape looks like, but how is that shape oriented with respect to the nucleus? Okay? Now, for each subshell you are in, the number of ways that the magnetic quantum number can show up, it goes from, so if you're in, say, the subshell like S, so whatever number S. Remember, S corresponds to 0, right? Corresponds to the number 0. So the only possible magnetic quantum number you can have is 0. But if you were in the P subshell, remember P corresponds to 1, the magnetic numbers you have go all the way from -1, 0, 1. So basically, depending on what subshell you are in, depending on what your secondary quantum number is, your magnetic quantum number goes all the way from -L up to +L. So if your secondary quantum number is 5, the possible magnetic quantum numbers you have are -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. You have a lot of them. So for L equals 5, your magnetic quantum numbers equal all of these guys. Okay? And again, each of those magnetic quantum numbers represents a different orientation of your subshell. So sort of putting it all together in a chart, when we are within the, when we have a principal quantum number of 4, we have 4 different subshells that we could possibly have. Let's make a little table. Number of orbitals. Okay. So when we are within the subshell 4s, that corresponds to a secondary quantum number of 0. So the only ML value is 0. When we are in 4p, that's a secondary quantum number of 1. So we can go -1, 0, 1 from -L to L. When we're in D, that corresponds to a secondary quantum number of 2. So we can go from -2 all the way up to +2. And when we are in F, we can go from -3 all the way up to +3. Each of these numbers represents a different orbital. So for 4s, we only have 1 orbital. But for 4p, we have 1, 2, 3 orbitals. For 4d, we have 5 orbitals. And for 4f, we have 7 orbitals. So within each of these subshells, we can then just figure out how many orbitals we have. So it's a lot of stuff. It's a lot of very specific stuff. And in fact, there is one other quantum number that we will be looking at in the next video. And with those 4 quantum numbers, we can uniquely define every electron in our atom. Every electron will exist within we'll have 1 pair of all of those quantum numbers. Okay, and we will discuss in upcoming videos. So thank you for watching. If you want more information about the tutoring services available on all 4 major ASU campuses and online, please check out tutoring.asu.edu/content/tutor-search. By going here, you'll be able to find a tutor on your campus that'll be able to help you with your specific class. Thank you again for watching, and I hope you have a wonderful day.